Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the second lecture of week 12, your lecture number 38, and in this lecture we are going to discuss about the mechanical sensors, including displacement and position sensors, level sensors, pressure sensors, flow sensors, and then finally strain gauges. So let's get started. We will be going to cover the mechanical sensors from your chapter 5 of your textbook number 2, that is by Curtis D. Johnson. And the instructional objectives of this chapter include various types of sensors for measurement of mechanical phenomena such as motion, force, pressure, position, etc. And after you have read the chapter and have worked through the examples and problems, you will be able to describe the three types of sensors for the measurement of displacement, location, or position, explain the operating principle of an LVDT, linear variable differential transformer, for the measurement of displacement, calculate the strain experienced by a wire under the influence of a force, and design the application of a strain gauge for the measurement of stress. So let's start with displacement, location, or position sensors. The simplest form of displacement sensors is using a potentiometric displacement sensor as shown in this figure. So you have a moving arm that is mounted on a fixed resistor R, and then you have a wiper that moves between different positions of this fixed resistor, and the resistance between these three terminals, terminal 1, 2, and 3, is proportional to the location of this jockey on top of this potentiometer. So simply the distance delta x will be translated into delta r. But in this case, you are not going to find out the displacement. You will only be able to find out the distance. So the magnitude of change in resistance will translate into the magnitude of displacement in either direction. This means that any signal conditioning circuit that converts resistance into voltage can be used for this purpose. We have discussed those circuits in detail, and we have to consider the self-heating power dissipation for any type of resistive sensors that we have also covered. Moving on, we can have a capacitive based distance sensor, and we have discussed this phenomena. So in case of a parallel plate capacitor, the distance between these two plates can be directly measured using this formula: C is equal to epsilon naught epsilon r A over D, where A is the overlapping area between these two plates, D is the distance between these two plates, epsilon naught is the absolute permittivity, and epsilon r is the relative permittivity or the dielectric constant of that particular material that is present between these two plates. And in case of displacement sensors, it is usually air. And so in one case, we can find the displacement, direct displacement in x direction by bringing these two plates closer or away from each other. And in another case, we can find the lateral movement of these two plates, and so the distance between these two plates will remain constant, while the overlapping area between these two plates will change. And if we have a change in area, we have a change in capacitance. So for signal conditioning of these types of capacitive displacement sensors, we can employ an AC bridge circuit, or other active electronic circuits can be used to convert the change in capacitance into change in current or voltage that can be further processed by your signal conditioning circuits. Then we have finally in displacement sensors the LVDT, or and the basis to an LVDT is a variable reluctance or a variable inductance based sensor. So in that kind of sensor, you have a fixed coil but a movable, permeable core that can be moved inside that inductor. So when this core is partially inside this inductor or fully inside this inductor, the inductance L of this coil will change, and that change in inductance can be translated into how much that core was inside this coil. The class of variable reluctance displacement sensors differ from inductive in that a moving core is used to vary the magnetic flux coupling between two or more coils rather than changing an individual inductance. So in this case, we were changing the individual inductance. But in case of LVDTs, we use the phenomena of varying magnetic flux coupling between two or more coils. So let's move on to the structure of LVDT. Over here we have a structure of LVDT, and here in the middle you have a primary coil, and on both sides of the primary coil we have secondary coil 1 and secondary coil 2, and inside these three coils is a movable core that has a mean position when it is completely covering the primary coil but is not coupled with the secondary coils, or it is coupled equally with both the secondary coils. So the induced EMF or the coupled magnetic flux of this primary coil with both of these secondary coils will be equal. This means that if we connect these two secondary coils in series opposing connection, we will get a zero output when this core is in the middle position or in the mean position and it has no displacement, and the flux linked to both these coils is equal. But as soon as the core is displaced from its mean position, for example, if it is moved to left, the flux induced between or the coupled magnetic flux between the primary and the secondary coil 1 will be greater than the coupled flux between the primary coil and the secondary coil 2, and that will give a difference in voltage output of these two coils, and as they are connected in series opposing connection, so their output will be a non-zero value. And what will be the form of that output? Here is the graph showing the core displacement from the mean position. So if it is displaced in the positive direction or the right direction, you will have a increasing voltage in the positive direction, and if it is displaced in the opposite direction, you will have an increasing voltage in the negative direction. Now a question arises that there is no positive or negative sign in AC voltages. An AC voltage has just a magnitude, and in place of that positive and negative sign we have the phase of that AC voltage. So this positive and negative sign is actually the phase of your output voltage, whether your output voltage signal was in phase with your input signal or out of phase. So if this is your input voltage, your output can be like this and your output can be like this. So your output can be in phase with your input, or your output can be out of phase with your input, and that phase will determine that in which direction your core was moving, and the magnitude of this output voltage will determine that how much that core was displaced in that particular direction. So thus by measuring the voltage magnitude and phase, one can determine the direction and extent of the core motion, and that is called the displacement. Now we know that it is difficult to measure the phase of an AC voltage because you have to compare the phase of input and output, and for that you need to employ a phase detector. So that can be simplified by converting this AC output voltage into a DC output voltage, and for that we can simply use some half wave rectifiers, two diodes as half wave rectifiers for both these secondary coils, and their differential output will now be ranging from in a DC will be a DC voltage ranging from negative X value to a positive X value. So this sign of that DC voltage will determine that in which direction your core was moving, and this magnitude X will determine that how much your core displaced in that particular direction. So the requirement of phase detection in case of AC signal can be eliminated if we simply rectify our output signal using two simple diodes. So these were the displacement sensors, different types of resistive, capacitive, inductive, and magnetically coupled displacement sensors. So let's move on to other types of sensors, that are level sensors. So level is usually made of a liquid, but the gas has pressure, solid has some stress or strain, but liquid, in case of liquids we want to know the level of that liquid in a particular container. So for that we can use different types of approaches. We can use some ultrasonic or infrared transceivers, one transmitter and one receiver, that incidents a wave of light or a wave of ultrasonic signal onto the surface of that liquid that is inside a tank or any reservoir, and then that signal is reflected back and is received by this receiver. So we can then process that received signal, and we can translate its magnitude or the time taken by this signal to travel to that surface and back, reflected back from that surface, and we can translate into the distance between this top of that container and the position of liquid level inside that container. So this distance x can be calculated based on two different approaches. The second approach is to put this transceiver inside at the bottom of that tank and use the same approach and use the phenomena of total internal reflection from the surface of that liquid. The third approach can be to use a concentric cylindrical capacitor to measure the level. So in that case, you have this outer cylinder as one electrode. These are two concentric cylinders, and between them is a hollow space, and that hollow space is open from the bottom. So the liquid, when the liquid level rises, it will rise between these two plates. So this outer cylinder is your electrode 1, and this inner cylinder is your electrode 2 of your parallel plate type cylindrical capacitor. And you know that C is equal to A epsilon over D. So in this case, D is the distance between two electrodes that is remaining constant. A is the area of overlapping area of these two electrodes, again that is remaining constant, but epsilon is changing because when the water level rises, the permittivity of water is different from permittivity of air. So epsilon will change and the capacitance will change, and that change in capacitance can be translated into how much portion of that capacitor was filled, and in turn that can be translated into the level of liquid inside that container. So there are different approaches. There are further approaches that can be used to measure the water level. One can be resistive. We can have a printed variable resistor here, and this water can be used to change the resistance of this printed longitudinal resistive sensor, and that change in resistance can be converted into the change in water level. Then moving on to the pressure sensors, we usually have the pressure sensors in the form of diaphragm based pressure sensors, where the diaphragm is an element that converts pressure into physical displacement. So that diaphragm is a thin flexible piece of metal or rubber or something, and when a pressure is applied to that, it deforms in shape, and that deformation in shape is actually a physical displacement, and that physical displacement can be measured by change in resistance, capacitance, or some other parameter of that diaphragm, and in turn that can be converted into pressure. Pressure can also be measured using LVDT. So you have a moving platform that is bound to the pipe in which you want to measure the pressure, and that movable platform is connected to an LVDT. So when the pressure is applied to that platform, the platform moves towards right or left, and that movement towards right or left is converted into a voltage signal that using an LVDT, and that change in voltage is converted into the displacement of that diaphragm or that platform, and that displacement is in return converted into the pressure that caused that platform to move towards right or left. And finally, we have flow sensors. In case of flow sensors, we usually want to measure the flow of any fluid. The fluid can be a gas, the fluid can be a liquid. And in case of both gas and liquid, we use different approaches. We can have a rotating vane that displaces from its mean point or mean direction based on the amount of flow that is passing through that pipe, or we can have a turbine based flow meter whose blades will rotate at a different speed when the fluid flowing through that pipe is flowing with a different flow rate. And again, in case of a floating flow indicator, we usually use it in case of gases. So when the flow of gas is increased, the position of this floating bead will change inside this column, and that position or displacement of this bead will in return tell us how much was the flow rate of that fluid inside this column. And then coming to the strain gauges. And these are one of the final sensors that we are going to discuss, and they are very, very important. We can say that these are the most important mechanical sensors because they are the most widely used ones, and they can be used in couple with other mechanical sensors. For example, in case of this pressure sensor, you can have a strain sensor connected to this diaphragm, and you can measure the strain that is produced in this diaphragm and convert that strain into the pressure. So we are going to discuss these strain sensors in detail, in which on which working principle do they work, and how they are coupled with any system of which we want to measure the strain. So starting with the basic, we know that the resistance of a metal sample is given by R is equal to rho L over A, where rho is the resistivity of that material, L is the length of that material, and A is the cross-sectional area of that material. Now, what if any of these three changes? The resistance will change. But rho is dependent upon the resistivity of that material. So any physical force on that material will not change the resistivity of that material. So this is out of question. We can either change the length or the area of that piece of metal. And in case of strain, the definition of strain is delta L over L. The change in length is called the strain. So this means that we are only interested in the change in length, and we will measure how much change in length is translated into how much change in resistance. So let's derive the relationship between this resistance, change in resistance, and the change in strain. Okay, so the strain is delta L over L of a metal. Now, how that delta L is produced and what is this delta L? The delta L is the change in length when a mechanical force is applied on a metallic wire or a metallic piece. When a force is applied and the length of that metal piece changes, this means that its cross-sectional area will also change, because there will be elongation if your piece was like this before and now it is like this. So it has to compensate in this cross-sectional area also to compensate for this elongation in length. So your new length will be L plus delta L, but your new area will be A minus delta A, because the volume of this piece will remain the same, because we are not adding or subtracting any material from that piece of metal. This means that your R naught is equal to rho into L naught over A naught. That was the mean resistance before elongation. So this is A naught and this is L naught. And your R after elongation will be equal to rho into L naught plus delta L over A naught minus delta A. And we all know that, let's call it equation 2. We all know that your volume will remain the same before and after elongation. So your volume before elongation was V naught is equal to L naught A naught, and your volume after elongation was L naught plus delta L into A naught minus delta A, and these are equal. So this implies that A minus delta A is equal to L naught A naught over L naught plus delta L. We can just rearrange this equation and we can call it equation number 3. So now putting this A minus del A into equation 2. So putting equation 3 in equation number 2, what we get? R is equal to rho into L naught plus delta L over L naught A naught into L naught plus delta L. And if we expand this expression, it will be equal to rho into L naught square plus delta L square plus 2 L naught delta L over L naught A naught. As the change in length is very small in most of the cases, so square of delta L can be approximated to 0, and your new expression will be R is equal to rho into L naught square plus 2 L naught delta L over L naught A naught. And again, further expanding this expression will become rho L naught square over L naught A naught plus rho into 2 L naught delta L over L naught A naught. So this square will cancel out, this L naught will cancel out, and our final expression will be R is equal to rho L naught over A naught plus 2 rho into delta L over A naught. If we multiply and divide this by L naught, or we just don't cancel this L naught from this expression, this can be written as, we can take this rho L naught over A naught as common, rho L naught over A naught into 1 plus 2 into delta L over L naught. This means that your R is equal to R naught plus delta R, and that is equal to R naught plus 2 R naught into delta L over L naught. Open this expression. This is 2 into rho L naught over A naught. That is your R naught. That is your R naught, and delta L over L naught is your expression that is coming with that. So this is the expression of R that you are getting, and this means that your delta R is equal to 2 R naught into delta L over L naught, and that will define the sensitivity of your strain gauge. And this delta L over L naught, you can see here, this delta L over L naught is actually the strain produced by that force applied on that metallic structure. So your delta L over L is directly converted into a delta R. I can write it this way: delta R is equal to 2 R naught into the strain applied. Your strain is directly linked to your change in resistance now. So this is the basic transfer function of your strain gauge. So let's come back to this. This relation is your relation between change in resistance with your strain directly. So moving on, we have another factor that is called the gauge factor of a strain gauge. And the gauge factor is the ratio of change in resistance over the actual resistance and the ratio of that quantity delta R over R with your strain. So delta R over R is the fractional change in your gauge resistance because of the strain, because of which strain delta L over L that is divided. So this gauge factor is just a quantity. If we are designing a strain gauge, or if we are choosing a strain gauge, we can see what is the gauge factor of that, and that can give us information of the overall responsivity of that sensor towards changing strain, fractional change in the length. So two effects are critical that should be kept in mind in designing the signal conditioning techniques for the strain gauges. The first one is a very small fractional change in resistance, and that require carefully designed resistance measurement circuits. A good strain gauge system might require a resolution of 2 micrometer per meter. So delta L over L is approximately 2 micrometer per meter for good strain gauges, and that is the required resolution. we can see from equation 12 that this would result in a delta R of only 0.48 milliohms for a nominal gauge resistance of 120 ohms. So your R naught was 120 ohms and your delta R was 0.48 milliohms. So this much small resistance change you have to detect. And the second effect that has to be considered is compensation for temperature effects, because strain gauges are effectively pieces of metal, and they are prone to their resistances are prone to changes because of the changes in temperature. So even a 1 degree centigrade change in temperature will result in a change in resistivity of a strain gauge, of a metallic strain gauge. We can see that how much can it affect if we consider the linear interpolation of RTDs, in which we discuss the change of temperature, effect of change of temperature on the change in resistance. We can see that for the same 120 ohm strain gauge, a delta T of 1 degree Celsius will result in a delta R of approximately 0.6 milliohms. So the change in resistance because of the change in temperature of just 1 degrees is even greater than the change in resistance that was actually due to the effect of strain. So that poses a huge problem. And to tackle both of these issues, both have a same solution. And that solution is to use a bridge circuit. A bridge circuit has a very high resolution, and it is an excellent circuit to detect small changes in resistance. And also, we can use a compensation sensor, a dummy strain gauge mounted in an opposing leg of that bridge circuit to compensate for the effects of temperature. And that configuration is called a one-arm bridge. So let's go to the one-arm bridge and let's see how it works. So here you have a bridge circuit in which you have two fixed resistors and you have two strain gauges. So this is R, this is R, this is RD, and this is RA. D stands for dummy strain gauge and A stands for active strain gauge. And now some power is supplied to this, and here is your V out or the detector. So how that dummy strain gauge and active strain gauges are connected on a beam on of which we want to measure the strain. So this is your active strain gauge that is connected along the length of that beam, and this is your dummy strain gauge that is connected transversely to the length of that beam. So when that beam bends in this direction, the length of this strain gauge changes, but the length of this strain gauge will not change. It will have effect only on these small minor areas, and there will be no delta L over L or no delta R because of the strain applied to this beam in this particular lateral direction. So this is your active gauge and this is your dummy gauge, and this dummy gauge is connected to the opposing branch of the bridge terminal, and this active gauge is connected here. So this is called a one arm bridge circuit or a one arm strain gauge measurement. So let's derive the sensitivity of this bridge with the strain with the change in resistance. We choose these resistors R that are equal to R. R1 is, this is R2, this is RA and RD. So R1 is equal to R2 is equal to RD naught is equal to RA naught is equal to R naught. So in case of zero strain applied, the resistance of this strain gauge is the R naught. And all of these resistances are chosen such that they are equal, and they are equal to the intrinsic resistance of that strain gauge with zero strain applied. Zero strain applied. So at this point, it is obvious that the bridge would be in a balanced state with a null output. Now let's see what if this RA changes. RA becomes RA naught plus delta R, or it becomes R naught plus delta R. Some strain was applied and the resistance of this active sensor changed. So what would be our delta V? Delta V will be equal to Vs, that is our supply voltage, into R over 2R of this branch. R, both of them are R, and when the strain is applied, none of these resistors will change. R2 will also not change, only RA will change. So that would be equal to minus R plus delta R over 2R plus delta R. And let's expand this expression. It will become Vs into 2R plus delta R minus 2R minus 2 delta R over 2 into 2R plus delta R. These will cancel out, and this will become delta V is equal to Vs into negative delta R over 4R plus 2 delta R, and that is equal to negative Vs into delta R over R divided by 4 plus 2 delta R over R. And then delta V will be equal to negative Vs over 4 into delta R over R over 1 plus delta R over 2R. And as delta R is much smaller as compared to the actual resistance, and again it is even divided by 2, so we can approximate this expression to be 0, and we can rewrite the equation to be approximately equal to negative Vs over 4 into delta R over R, as this will become just 1, and this will be our final relation, that is equal to delta V. So a change in resistance of delta R due to a change in length of delta L will result in a change in voltage delta V that is related to each other with this expression. And if we further write it in the form of gauge factor, that would become, as the gauge factor is delta R over R over delta L over L. So that would be equal to, this equation 1 would be equal to delta V is equal to negative Vs over 4 into strain into the gauge factor. So this equation relates your change in voltage output of that bridge circuit with your strain and your gauge factor directly. So this is for a single arm bridge. But what if we use a dual arm bridge and we use 2 dummy cells and 2 active cells like this? All 4 are now the strain gauges. This is RD, this is RD, this is RA, and this is RA. This is your Vs, and here you have your output detector. So first let me show you how these dummy cells are actually connected to the beam of which we want to measure the strain, and then we'll move on with the actual derivation of the output of that dummy cell. So here, as shown in your book, this was the configuration for the single arm bridge, in which we have one dummy cell and one active cell, and here we have the configuration in which we have 2 dummy cells and 2 active cells. So let's suppose this is the beam on which we are applying the force, and due to the application of that force downwards, this beam's length will change. So this top active cell, that will expand, and this bottom active cell, that will contract, that will expand in an other direction. So that will be effectively a contraction. So this is expanding and this is contracting, and both of these dummy cells have no effect of this strain on their resistance. So this means that the resistance of this active cell will be increased by delta R and the resistance of this active cell will be decreased by delta R. So now let's come to the derivation of the relationship of voltage with the strain. So here the expression of del V will be equal to Vs into R plus delta R over 2R plus delta R minus R minus delta R over 2R minus delta R. So let's expand this expression and see what is the result. And this gives us delta V is equal to Vs into 2R square plus 2R delta R minus R delta R minus delta R squared minus 2R square minus R delta R plus 2R delta R plus delta R squared divided by a plus b into a minus b, a square minus b square, so that is 4R square minus delta R square. And we can see that this 2R square is cancelled with negative 2R square. This 2R delta R is cancelled with negative R delta R and negative R delta R. This positive delta R square is cancelled with negative delta R square, and we are left with del V is equal to Vs into 2R delta R over 4R square minus delta R square, and this delta R square can be approximated to be 0, so that is equal to Vs into 2R delta R over 4R square. And again this R is cancelled with this square and this becomes 1 over 2, so that is in return equal to Vs into delta R over 2R is equal to delta V. Call it equation 2. And let's compare these two equations, equation 1 and equation 2. Your equation 1 was delta V is equal to negative Vs over 4 into delta R over R, and your equation 2 is Vs over 2 into delta R over R. So your delta V has increased by 100%, or it has become 2 times. So this means that your sensitivity has doubled if you choose a dual arm configuration in which you have 2 active sensors and 2 dummy cells. So to mere very small changes in resistance in case of strain gauges, we can use these configurations to improve the sensitivity output, the delta V of our bridge circuits, by using multiple active sensors instead of just one. And lastly, coming to how these dummy cells are compensating for the temperatures for which they are being used, let's see here. If temperature rises and the resistance, if the bridge was at null, and the temperature rises, so the resistance of both RA and RD will rise, and they will rise with the same magnitude. So del V will be equal to R over R plus delta R, and VB will be equal to R over R plus delta R, and that would be equal to 0. Bridge was at 0. So no matter how much this delta R increases due to temperature, it doesn't matter, because the null condition of your bridge will not be disturbed, and even if it is not at null condition, so this delta R will be added to both of them equally, and as they are being subtracted at the output, because we are getting a differential output, so their effect will be automatically cancelled. So that is fairly simple in case of a single arm bridge. What happens in case of a dual arm bridge? So we have a bridge like this, and here are our dummy cells and here are our active cells. So again, let's assume that this bridge is at null condition initially. So if there is any change in resistance due to temperature, all these four sensors will be affected equally, and the net effect at the output will be 0 volt. No matter how much temperature increases, the resistance of all these four sensors will increase or decrease equally, and the net effect of them will be cancelled out at the differential output of this bridge also, as we can clearly see here in this equation. So that's how you compensate for temperature changes for very small changes of resistances in case of strain gauges, and you get a fairly high sensitivity in terms of voltage output in case of a dual arm bridge for a strain gauge. And lastly, about the strain gauges, there are just some good design practices that are used when we have strain gauges connected in our bridge circuit. So we use these kinds of mechanical connections that are called slip rings to connect our bridge with our actual signal conditioning circuit. And why they are used? What are slip rings? They are similar to the bushes in a DC motor. They are needed for rotational loads attached with the strain gauges. So when your strain gauge is rotated or it is twisted, the resistance of these wires might also be affected. And to stop the resistance of that wire from changing because of that applied rotational strain, we use slip rings so that the rotational strain or the rotational force does not act on the resistance of that wire that is connected to that strain gauge. They are mounted on a shaft of the rotating object to make the axis of rotation common for both of them, and several bushes are attached at the outer shell of these slip rings to transmit the signal without twisting your wires. The disadvantage of using these slip rings is dirt can be accumulated in the connections, in these mechanical connections, and it can cause major fluctuations in resistance, so they have to be maintained and calibrated very frequently. The sole purpose of using slip rings is to connect the Wheatstone bridge containing the active strain gauge with the recording instrument and power supply without twisting your wires and without damaging your circuit. So we have discussed in detail about different types of mechanical sensors that are used in our industry and our daily lives, and we have particularly explored in detail about the strain gauges because they are very important class of mechanical sensors. And we have also discussed that these mechanical sensors are also giving their output in the form of change in resistance, capacitance, or voltage, or any other quantity, just like in case of temperature sensors. And same kind of considerations have to be kept in mind while designing the signal conditioning circuits for these mechanical sensors, as was the case with temperature sensors. So effectively, once we have covered all the types of sensors based on their working principles, not based on the measurement objective, and we design the signal conditioning circuits for different types of sensors based on different working principles. For example, capacitive sensors, resistive sensors, very small changes in resistance, changes in voltage. We are actually completing that whole category of sensors, not that just parameter. So we don't care whether the resistance was changing because of the change in temperature or strain or change in light intensity. We are only interested in the change in resistance. How much was the change in resistance, and which considerations we have to keep in mind while designing the signal conditioning circuit for that sensor whose output is in the form of change in resistance. Why that resistance was changing, we are not concerned about that. So designing the signal conditioning circuits for temperature sensors almost completed our signal conditioning design requirements. And after discussing the sensors, mechanical sensors in today's lecture, our sensors based portion is now complete. From the next lecture, we will discuss some basic terminologies and some additional concepts related to instrumentation, some very like significance and noise and interference. And then we will move on to solve some design problem based examples, and we will try to find the solution of different types of sensors and different requirements, application based requirements, and how to tackle them and how to design the analog and digital signal conditioning circuits for those applications. So that's it for today's lecture. See you in the next live session, inshallah. Till then, take care, stay safe, Allah Hafiz.